And the questions that I want to touch in this presentation is what does our galaxy look like in gravitational waves? What gravitational wave sources tell us about our galaxy's structure and formation? And for instance, what is the merger rate of galactic gravitational wave sources as compared to extragalactic ones? Our Milky Way really hosts a variety of these tight binaries that emit gravitational waves. They come in different flavors. So the majority will be of double white dwarf type, whether detached or accreting. We will also know ultra-compact X-ray binaries that are accreting neutron stars. We know binary neutron stars, and so on. And these binaries are millions to 1,000 years away from the merger. So they will emit this nearly monochromatic continuous gravitational waves. Their waveforms are the simplest we know. That we can describe with 8 parameters that I have here. So the amplitude, frequency derivative, the chirp, and then the angular parameters. So the sky coordinates, inclination, polarization phase, and binary orbital phase. No, and you well know that the frequency of gravitational waves for this source depends is twice binary orbital period, and the amplitude scales with these 3 parameters, right? The chirp mass, frequency, and the distance. And if we plug in typical numbers, for instance, for white dwarf binaries, we get these amplitudes of the order of 10 to the minus 22, which is within LISA reach. And just for your reference, the typical change in the binary's orbital period due to gravitational wave radiation for our galactic sources is of the order of 1 nanohertz per year, so extremely slow compared to LIGO sources. And in the LISA field, we really like to show our binaries on this plot. So you have here gravitational wave frequency. This is the LISA sensitivity band. On y-axis, you have this amplitude or strain parameter that can be intuitively interpreted as the strength of the signal. On the top, you have the respective binary orbital period. So we will detect binaries between 2 hours to minutes orbital period. This is expected LISA sensitivity. So all the sources above this curve are detectable by LISA and below are not. And now let me show you all of those types of binaries, the predictions for all of those types of binaries that we reviewed in the LISA astrophysics white paper that has been recently published as a living review. So the most numerous type of source will be of this will be double white dwarf binary, and this is simply because, right, these stars like our sun are the most common stars in the Milky Way. They eventually turn into white dwarfs, and so this is the most abundant double compact object in the Milky Way. And on the other hand, these stars are also evolve on a very long time scales, much longer than stars that eventually turn into black holes and neutron stars. So they stay in our galaxy also for a long time. And here I will be showing you an upper limit on our estimates. So we expect tens of thousands to be detectable with LISA. And I'm showing you only those with a certain signal to noise ratio. And this is why you see a gap here between the cloud of the gray dots and the LISA sensitivity curve. And then, of course, we'll have other types of binaries, so white dwarf plus with the neutron star companions. They will be a couple of orders of magnitude less abundant. And just to note that these bars are on a logarithmic scale, so that I could actually compare them. And the double white dwarfs will be much more numerous. We also have, we will also see binaries here in yellow that you may not see as well. So these are stars, white dwarfs or neutron stars with the subdwarf companion. So a still living star that is still burning fuel in the core, but it was stripped out of its envelope. So we can now fit it in a tight orbit that emit gravitational waves in the LISA band. So this is why we are seeing them in this lower frequency part. We'll also see some double neutron star here on the top, and of course, binary black hole as well as binary neutron stars and black hole. And you see that all of those will be orders of magnitude less numerous than double white dwarfs. So I will focus on the double white dwarf binaries from now on. And we will see these binaries not only as individual gravitational wave sources, but also the majority of this population would just blend to form this unresolved stochastic foreground that you can see here. So I won't talk much about it. You can ask me afterwards if you wish. But there is also some information on the overall galactic population of these binaries in the foreground as well as in resolved sources. And finally, also let me mention that the points that I showed before are theoretical predictions, but we know some binaries that that exist in this regime. We have already discovered them with electromagnetic observations, and these are the points that I'm showing you here. And I'm showing you Gaia here again, because thanks to Gaia that provided us distances to these binaries with the second data release, we were able to put the error bars on their amplitude of gravitational wave signals. And so the idea is that because we know we can predict their amplitude, frequencies, and so on from electromagnetic observation, we can potentially use these binaries to test LISA performance in one way or another. So we usually call them LISA verification binaries. And again, the majority of these binaries are made of two white dwarfs, but there are some, for instance, this is a ultra-compact X-ray binary, and we have a couple of those sub-dwarfs with the white dwarf companion. And now let me show you some of my favorite plots to show you the potential of LISA as a survey for this binary. So here I will show you the distance from us as a function of the gravitational wave frequency for 3 example binaries. So the yellow will be signifying a double white dwarf, then the orange something like a double neutron star or so, and the red there is a binary black hole. And these are the horizon distances for these types of binaries. And basically, the main idea that I wanted to show is that we can see these binaries everywhere, like to the edge of our galaxy that is over here at around 300 kiloparsec. If they are of a binary neutron star type, they are visible a bit further out through the local group, and binary black holes we can see as far as Virgo cluster, and if they are even more massive than this, even further out. And what I will do in this plot is to show you something that I call completeness as a function of frequency. And here I define completeness as the number of detected binaries by LISA divided by the total. And to compute this ratio, I used some theory and observations-driven models. And you can see here that all of my curves are rising very steeply at around millihertz frequencies. Oops. Oh, this is not me. Okay. And at a couple, 2-3 millihertz, right, we're reaching 100% completeness. So what this means that we see all binaries that are out there in our galaxy. So we can simply count how many sources LISA can see at these frequencies to know how many are out there in total. And to be honest, even at the lower frequency, we know that this binary is evolved by gravitational wave radiation. So we can extend these constraints to lower frequencies as well. So what does it mean? For this, I wanted to use the example of type 1a supernova. So these are explosions, right, of white dwarf stars that are amongst of the brightest supernova or transients that we know in the universe. We know that this should be a white dwarf, but we don't. But since white dwarfs do not explode on their own, we believe that there should be a companion that makes the white dwarf explode. And the dilemma in the field that has lasted already for decades is what is the progenitor, what is the companion of the white dwarf? On one hand, we have a channel that basically has any sort of living star, so main sequence, giant, subgiant star. And via accretion, you grow your white dwarf to a Chandrasekhar mass that leads to the explosion. And in this other channel, you have two white dwarfs that are brought together by gravitational wave radiation. And, an explosion happened in one way or another. So this is a historical perspective. Right now, the picture is much more complicated, but it's useful for me to divide it this way because we can probe with LISA this double degenerate channel, no? Because we see all of those binaries made of two white dwarfs everywhere in our galaxy in a complete way, so that we can really test it with LISA observations. So first of all, right, coming back actually to here, we can count how many binaries LISA can see. That already provides us a constraint on whether there are enough of double degenerates in our galaxy or not to make up for all type 1a supernova rates. But we can do better. We can measure these binaries chirp masses, and this is what I will show you here. So you have a fractional error on the chirp mass as a function of gravitational wave frequency. And again, I decided to show you 3 examples. Carefully selected. So the top yellow one is a binary in which the primary can explode as thermonuclear transient, but is not massive enough to make a type 1a supernova. And the other 2 examples are where the primary is massive enough to result as a type 1a supernova. So let's see what we can measure with LISA. So again, here at a couple millihertz frequencies, we just start in measuring these chirps from which we can recover the chirp masses, but already going to 4 and less millihertz, right? We can start placing constraints to sub% level. And from here, we can translate those constraints into primary, secondary mass parameter space. So here I'm showing you, again, the same 3 examples. Let's focus on the red one, which is the easier. So this is the more massive one. So this shaded region represents the constraint at 2 millihertz, where we just starting, we are getting into 10-ish% constraints. And going down to 4, 6 millihertz, we collapse to this dotted line. So basically, for the type 1a question, what matters is the constraint on the primary mass. Okay, sorry, I have a message from Zoom. So what matters is the constraint. So my Zoom disconnected. I'm not sure. Oh, okay. Okay, so you can see, and hopefully everyone can see. Okay, sorry for that. No. So I'll try to reconnect. Okay, I think that I don't have Wi-Fi. Yeah, yeah, but I have a surprise, so I'll do something else. Sorry, I'll share. Okay, just a second. I'm almost there. Come on. Okay. Okay, so sorry for that. So to restart, right, we can translate constraints on the chirp mass into constraints on the primary mass that you can read from the x-axis. So again, looking at this red example, right, what we will be able to say is that the binary is at least 0.7 solar masses. What does it mean? So based on 3D hydro simulations, we know that we can divide this parameter space into categories, very broad categories. So binary primary masses that are below 0.5 solar masses, they do not generate thermonuclear explosions, so they do not detonate. So if we place a constraint of in this regime, right, that would mean that we won't see an explosion. While in primaries of above 0.6 or so, in 3D hydro simulations, we know that they can detonate and produce some sort of thermonuclear transient. And if the primary is above 0.8 solar masses, that results in type 1a supernova. So what this means is that from the LISA data, we will be able to put a flag which of these binaries will eventually detonate and produce thermonuclear transient or type 1a supernova, which I think it's really cool. Although this will explode in 1,000 years from when LISA will detect, but maybe astronomers of the future will be able to observe those. And then we can measure the merger rates of this binary. So here I will show you the fractional error on the merger rate as a function, again, of gravitational wave frequency. I picked 3 examples of the measured merger rate of type 1a supernova in external galaxies here. So, and this is just as a reminder, here you see the formula that is underlying this calculation. So if we consider only the Poissonian error on the count of how many binaries LISA will see, this is how the merger rate error will go. We have less binaries at higher frequencies, and so our errors there are larger. And if we add, of course, on top of that also the measurement on the chirp mass, which dictates when the binary will merge, we have these solid lines. So at around, again, 4 millihertz or so, we have a sweet spot where we can measure merger rates to few to several %. And the idea is if that is comparable to type 1a rates in external galaxies, that would be a strong indication that this is a double degenerate scenario. And finally, also let me show you what if one of these double degenerates actually explode while LISA will fly. And there is a small but measurable percentage chance to this to happen within a full 10-year mission lifetime. And the question that I looked here is how the gravitational wave signal will look like of this type 1a explosion in our galaxy. So here I had to assume some sort of a detonation mechanism. there are multiple models, and the one that I used called double detonation. And this is, in my non-expert understanding, is one of the leading mechanisms out there in the market. And what happens is that we are now looking at the snapshots from a 3D hydro simulation of 1 plus 0.7 mass carbon oxygen white dwarf. So here we are 10 seconds away from the type 1a explosion. And the secondary, which is this fluffier white dwarf, starts transferring the mass onto the primary. What happens here is that the conditions are such that as the stream hits the primary, we reach the condition for the detonations. And this detonation happened on the outside in the helium shell that ignites and then engulfs the primary white dwarf. You see that this happens in a matter of like 1.3 seconds. And in a few extra seconds, the primary burns completely. So we produce type 1a supernova. This whole thing burns in a couple of seconds and leaves no remnant. So what gravitational wave comes from this? So what we are looking at here is the time. At the bottom panel, you have gravitational wave frequency. So this is the output from the simulation. At 100 seconds away from type 1a, we are in the regime of 90-something millihertz. So it's really on the edge of the LISA band. And the binary shrinks by a few millihertz. And on the top, you see that until the very end, this binary emits this expected almost monochromatic clean signal. And as the type 1a supernova happens, we remove one companion from the binary, so the signal shuts off. And this, constant strain, it basically comes from expanding envelope. So let me put this into a broader context of multi-messenger detections. So if we see this scenario in which we see monochromatic gravitational waves, and then a prompt electromagnetic emission that would indicate that this is a double degenerate scenario. If the electromagnetic emission is fast following the gravitational wave radiation, then it would mean it's something dynamical like this double detonation channel that I showed you here. Because in double detonations, you don't need massive white dwarfs. It is unlikely that we will see any neutrino associated unless the supernova is very close. However, there may be a scenario in which we see this monochromatic gravitational wave disappearing and then no electromagnetic or delayed electromagnetic radiation. And this may be, again, this should be a double degenerate scenario, otherwise we don't see gravitational waves. But in this case, we know that some of the the detonation models that are more of this classical super Chandrasekhar, where you basically bring the two white dwarfs together to form a total mass of higher than 1.4 solar masses. In these scenarios, you have delay times for the electromagnetic radiation up to tens of thousands of years. So we may just not see it. And in these cases, actually, the densities and the temperatures in the white dwarf is high enough to produce significant neutrinos. So we may have some association there. And if we see only electromagnetic radiation, right, we are sort of where we are now. So this is not a double degenerate case, because otherwise we would see a disappearing LISA signal, or it can be a double degenerate case, but with this super long delay that means that we just missed it with LISA. And again, depending on the white dwarf mass, the neutrino association may be possible or not. And then let me now, so this was regarding the what we can learn about the binaries and their explosions, but let me tell you a little bit more how we can use LISA detection to study our own Milky Way. So now let's look at our galaxy from the top. This is just an artist representation where you have, like this is how we believe our galaxy should look like, right? It has a central bar bulge structure, then the spiral arms. And this is LISA. Here, LISA is not to scale at the sun position. And let me now overplot LISA detectable binaries here, color-coded by frequency. And this is one of my favorite plots because you can really see that we can use these binaries to trace the structure of our galaxy, and we can trace the structure not only in the central region where electromagnetic observations struggle to see at the low latitudes because of the dust extinction and stellar crowding, so we can really look through the galactic disk, but also map the other side of the galaxy, which is even harder to do with electromagnetic observations. And it turns out that LISA sky localization and the distance measurement are good enough to then constrain the galactic scale parameters. So, for instance, we did some studies that assume an analytical expression for the distribution of the double white dwarf binaries. And what we did is to try to simulate LISA observation, LISA 3D position errors, and then recover back the shape of the galaxy that we initially put in. And we find that we can reconstruct the shape, the scale parameters of the bulge and the disk, the axis ratio of the bar, and also its length and orientation. And just to put this constraint into context, I wanted to flash this some of the plots that are using different stellar tracers to look at the Milky Way total mass, then scale radii, and the bar geometry. So these are using any other living stellar tracers, right, not gravitational waves. And you can see that there is significant scatter on all of these parameters. So there is plenty of space for LISA to provide an independent constraint on these parameters using a completely different messenger, right, gravitational waves. And because this is the last talk, I wanted to entertain you a little bit with some gravitational wave-based music. So I wanted to tell you a little bit about the project that I work in collaboration with the composer, pianist, and visual artist to sonify this simulated LISA data. And here, of course, as in the LISA data analysis, no, the problem is how do you play all these binaries at the same time? And we really wanted to keep the scientific fidelity of the amplitudes, frequencies, and spatial distribution of these binaries. But at the same time, our constraint was to come up with the music for a piano, right? So only two hands. And so we come up with a strategy that separates the signal in time. And that basically just by drawing random trajectories from in the Milky Way, and then play the sounds along those trajectories within some established audible volume. So the music that you will hear is really like trajectories in this LISA simulated galaxy, and we will hear frequencies and amplitudes of the coming from the simulations. So I'll play a few bits. And just a warning, this is, of course, a science-inspired music, so it may not be, of your favorite type. So be ready. So it's not going. Come on. Okay, yeah. of the Milky Way. And again, I left here the color so that you can relate a little bit to the frequencies. So I'll stop now and I'll share my favorite bit, which came like quite melodic. So here, I think we are somewhere in this region, right, where we have like this lower frequency binaries, but also some high frequency nodes. And finally, we also have some pieces for regions where we have only, yeah, a bit more. Yeah, so here we are probably somewhere like really on the outskirts. Okay, so I hope that entertained you a little bit and woken you up before the discussion. And if you want to hear the rest of the tracks, you can find them for free over this link. So just to start wrapping this up, so I showed you that we can see these binaries everywhere in the galaxy, but actually we can go a little bit further out into the satellite galaxy. So what you see here is our Milky Way now in this different coordinate system. So the red and orange is the Milky Way plane. And here the points and stars are known satellite galaxies. And the ones where we have more LISA detection that in the Milky Way background I highlighted in blue circle. So for instance, the Magellanic Clouds will be like really spatially resolved galaxies in the LISA sky. So here you see a simulation compiled by a master student that I supervised, and we took the Gaia view of the LMC, which you see in grayscales, and the LISA contours are in red. And the other galaxies, so we may see some binaries in the Sagittarius dwarfs and the Sculptor galaxies, but this is really the most nearby and massive satellites to us. So to recap, I showed you that we can see population of stellar fossils in binaries made of white dwarf neutron stars and black holes as well. And those are just inaccessible in this complete way with electromagnetic telescope. We can, based on the LISA data, even just by counting how many binaries LISA can see, we can contribute to the type 1a progenitor dilemma, and we can map our galaxy and its satellite using these white dwarf binaries. And there is of course so much more than LISA can do, and I refer you, as Antoine did, to the LISA Red Book that is the latest, most complete paper that you can find online. And so I'll leave you with my questions that I started with.
Any questions? Okay.
So, thank you for this exciting talk and music. LISA will undoubtedly do something extraordinary with the white dwarfs, allowing us to reconstruct the potential of the Milky Way. But we already have the verification binaries. So what can we tell about supernova 1A rate starting from the verification binaries that we have right now?
Yeah, so I think that verification binaries that we have, those are the known LISA sources. They are on a low mass side. So they are those that are, like most of them, unlikely produce thermonuclear transients. So the constraint comes from the outside the LISA band. So for instance, in spectroscopic surveys, we can see double white dwarf candidates and derive type 1a merger rates. And those studies yeah, actually I can account for the entirety of the type 1A rates that we observe, but it is still an open debate, right? Because we don't until recently, and like we haven't, yeah, there is still no connection between the progenitor and right, the transient. So I think that in the field the debate is really open. Yeah.
Sorry, but then just to be sure, you say that based on what we have, the double degenerate can be the entire. Yeah. Okay, thanks.
Yeah, thanks very much for the very nice talk. I have also one question on the 1A rates. So you mentioned the 1A rates, merger rates, to to constrain this single degenerate versus double degenerate scenario. And so correct me if I'm wrong, but I think so. So also one of the main arguments favoring the double degenerate scenario over the last, let's say 10 years or so was that people measuring basically the delay time distribution with respect to star formation and showing that it's basically a t to the -1 delay time distribution, which nicely matches with the observations of 1As. So this is just a curiosity. Now that you can map out basically all the white dwarf binaries in the Milky Way, as you showed, I was wondering whether you can correlate this with whether you can basically extract the delay time distribution with respect to star formation in these different regions, which would be a good argument on top of just the bare rates to show that empirically there's a second aspect that matches with 1A observations.
Yeah, so to extract that, I think we can do it if we use a model, right, for the binary evolution. So if we can narrow down that, then we can disentangle star formation from formation efficiency, whatever. But at the moment, I think that the measure uncertainty relies into the binary evolution, and for double white dwarfs, we don't have such like a big uncertainty. So I think that for LISA, we have uncertainty within like an order of magnitude between different models. And thanks to verification binaries, we can actually rule out some of the models already, those on the very low side. So if we can improve binary evolution, then we can disentangle star formation and the binary evolution to recover the delay time. Or we can do it in a Bayesian statistical way.
Thanks a lot. I mean, you showed this impressive map of all these binaries, and I was wondering how many would be too much for LISA. I mean, how many? Is there a risk that there are too many and the frequencies would all overlap and you wouldn't be able to resolve them? And how far do you think you are from that upper limit somehow?
I think that so there is already a problem, right? That there are a lot of them, and this is why we have this foreground. So I think that currently we are expecting tens of millions of binaries in the LISA band. But again, we have some uncertainties in the models. Some models actually predict very few binaries in this regime. For instance, if you have the shrinkage of, like some models have the pileup binaries outside the LISA band, and so you don't have the foreground because there are not enough of them. But again, then coming back to verification binaries, those models do not reproduce the number of verification binaries. So they should be, we are probably in a situation in which there will be some foreground. But it is still uncertain how much of it there will be. And I think that if we are able to extend LISA for more than for some years, right, this foreground will shrink and we will see more and more of the population. So I think that we are able to to recover a good fraction, and right, we can measure their parameters in this regime, in the few millihertz, and that's already enough for doing all the science that I showed. So I think that we will be in a good, of course we can see more if possible, but there will be a lot of science coming out of this, yeah.
Hi, thank you very much for your really nice presentation. I have a question, a general question, naive, concerning the supernova type 1a. Do you have any ideas or any suggestions concerning the initial stars in the binary system, how they come from? There is from objects which born together, or they just meet in the universe at a moment.
You mean like the channels as we discussed for?
Exactly.
Okay, so I know, I'm actually not sure if, can we produce dynamically? Yes, you can, for instance, you can have triple systems, right? And you can have this close encounters. I think that actually triple channel, so you have the inner binary and a third companion that can help you to produce a type 1a. They are can be of a comparable contribution as this just isolated binary. So it is an open question, and it would be interesting to to investigate. And dynamical channels, I'm not sure like if they can make up for all merger rate, but I would expect maybe they ought to be a bit more rare, but honestly, I don't know. Yeah, so it is still possible to produce type 1a supernova from either isolated binary evolution in the field, or some sort of multiple systems or clusters, or even galactic tide that help the two come together. Yeah, but yeah, I think it's still all on the cards. Like,
Thank you very much.
Last question.
So coming from naive question coming from ground-based gravitational waves, when we search for continuous gravitational wave sources, we have to worry about detector artifacts that are at single frequency, at stationary frequencies. I have no idea what happens when you set your direct detector into space. Do you also have to worry about stationary artifacts that could be at single frequencies and could mess up your searches?
I think, well, maybe Antoine knows better. But we have some glitches in the data.
Yes, we have some glitches in the data, but we don't have this kind of spectral line. We may have some of them. We observe one of them in LISA Pathfinder, but we don't have, as it is in LIGO, Virgo, we don't have this large number of lines. So we don't expect to have too much confusion between this line and galactic binaries. And in addition, because LISA, this is permanent source and LISA is moving around the sun, then you can detect the modulation very clearly. And if you see this modulation due to the motion of LISA, you can clearly identify the source.
Okay, brilliant. I'll keep my question for later. So we're going to move on to the panel discussion. So can Michaela and Abbas and Valeria all come and sit at the front?